Yes, I'll turn that on. Thank you. Well, find the right key to hit. Okay, as soon as that comes up, we are recording, but we'll start talking. Let's just do a quick review on where we are and where we're heading and what we're going to happen, especially today. We'll continue in chapter 16 until 3:15. 3:15 we'll start the second lab, and hopefully we'll finish that before 5:15, and that will give you plenty of time to do the second test, and then when you finish the second test, you can go. And this is Chelsea. What's that? Oh, I did want to ask this, though. Have any of you received anything about a tornado? Okay, have you heard any?
Tornado watch.
They said all the Lawson campuses were under tornado.
Okay, but they haven't issued a alarm. I mean, that hasn't sounded yet, has it? Okay, good. Okay, good. All right, it's just a watch then, right?
Yeah. It's supposed to start around 2:30.
Okay. All righty. Okay, well, hopefully that won't interfere with us in it. But until then, unless that happens, we are going to continue in chapter 16 until about 3:15, and then at 3:15 we'll start the lab if we're here and everything, and on chapter 15, and then hopefully we'll finish that by 5:15. If we finish it early, you get to start your test early. If you start your test early, you can leave whenever you start your test, you can leave when you're through. So that's how we'll plan to go today, unless something happens with, hopefully there won't be any tornadoes. It's just a warning or watch now, I guess it is. Whatever the lower level is. Okay. Any questions on anything we've covered so far? Yes? Okay, I can't hear you. Say again.
Is it okay to take pictures from the slides?
Oh, absolutely. Whatever you want to do. Yeah. All right. Yeah, you can certainly take pictures, whatever. Okay. Where we left off last time was approximately on page 410. It was called Revolution in the old text. In the new edition, it's called Orbit. Okay? And I think that pretty much follows the same thing. So what is the orbit, or the revolution of the Earth? It's Earth's movement around the sun. Okay? Our orbit defines the plane of the ecliptic. Okay? Now, let me get my visual aid back out here. All right, here's Willie, right? Okay. CC hasn't made it back yet. All right. Now, I think Rachel's going to be the sun today. She's really bright. Okay. So, here's the Earth relative to the sun. Now, as we go around the sun, notice that, okay, right about now, probably the sun's pretty close to being over the equator. Okay? But as it goes here, the sun is dipping down here, and then when you get over here, it's back at the lowest point here, and then when you get back to around where Ray is, it's back at the equator, then it starts rising, and when you get back over on this side part, the sun is here. What you just mapped out is the ecliptic of the sun. Okay? It's basically what the sun is eclipsing behind you. Okay? So when I'm looking here, any stars which are back there where, say where the window is back there, they're being eclipsed by the sun, I can't see them. So therefore everything there that's on the ecliptic. Is that in anyone's way here? Is that blocking? Okay.
No.
Let me make sure I mark CC here. Does anyone else come in since I called roll? So that's what it means. The orbit defines the plane of the ecliptic. Okay? It's below the equator sometime, on the equator, above the equator. The ecliptic is the apparent path of the sun through the heavens as seen from the earth. Okay? And here we have Trey, right? Okay. All right. By the way, the first page is all here. Way to go. Waiting a few from the second page to arrive. Okay. Now, don't get these two words crossed up. Ecliptic is the apparent path of the sun through the heavens as seen from the earth. So, in other words, what the sun seems to be eclipsing the stars back there now, then the stars over here, later stars over there. So it's eclipsing different parts of the sun, of the heavens. Okay, this is second. Kara, yeah, I was just trying to find your name on the roll here. Okay, so that's the ecliptic. Now the Earth is also in an elliptical orbit, not a circular orbit. Okay, and what that means is late August, we are moving more toward the sun because at the early July, we were as far from the sun as we ever get. Okay, so believe it or not. Then when we get to January, we're as close to the sun as we ever get. Now, did we get over this slide before? I know I said that before, but we didn't use this slide before, did we? I don't think so. This is where we left off. And that's because we have a slightly elliptical orbit. Okay? We're not a perfectly circular orbit. And as I said before, the closest to the sun, if it was a great distance, yeah, we would notice difference in temperature. Probably someone can, since in January, this is actually January here, in January here, just a little past that, the sun is as low in the sky as it is, but we're as close to the sun as we ever get. So that sort of moderates us. And then in July, when we're over here, and we're farther from the sun, but we're tilted toward the sun. So again, it moderates some, and we get more direct radiation. On the other hand, the southern hemisphere is closest to the sun here, and they're tilted to the sun, and over here they're farthest from the sun and tilted away from the sun. So if anything, the southern hemisphere should show a little more marked extremes in temperature. I don't know if it's really all that noticeable. There's another thing that moderates that. Most of the northern hemisphere, a lot more land is visible. Southern hemisphere, a lot more water is visible. Water is a equilibrator, you might say. It takes more energy to heat the water, or once it's heated, it takes longer for it to cool. Okay? So that's called the specific heat of water is so great. Now, Earth receives about 6% more solar radiation energy in January. That's the entire Earth. Mostly received by the southern hemisphere because they're pointing toward the sun as well as closer to the sun then. Okay? And so that's why I would think if anyone would notice it, it would be more the southern hemisphere than us. Okay? That's our revolution around the sun. Now, this is a greatly exaggerated model. it's not this much closer than that. I mean, this looks like it's almost twice as far away in June as it is in December. Not that extreme, okay? But they amplified it or exaggerated it so you can have a good idea what's going on. Now, and we pointed this out before too. Now notice here, our scales are really pathetic here. When we're closest to the sun, I mean, when we're closest to the sun, we're tilted away from it, so that moderates. But when we are tilted the maximum, the sun is overhead at what?
23.5.
Yeah, 23.5 degrees south. What do we call that imaginary line? The what? I hear one of you. Okay. Okay. It's called the Tropic of Capricorn. That's the 23.5 degrees south. And what is this one up here? Tropic of Cancer. And that's where the sun is directly overhead on or around the 21st or 22nd of June, because we're tilted as much there. So because our axis tilt is 23.5 degrees. And on March 21st, or 20th, 21st, September 22nd, 23rd, what are we? The sun is directly over the equator. Everywhere, okay, as it spins. And then we have, that is right at the turning of, for northern hemisphere, winter to spring to summer to fall, to, okay. And what is that day called? March 21st or 22nd, 20th or 21st? The equinox. Both of these days are equinox. It's called the vernal equinox. This is called the autumnal equinox. Okay? These are the, now, they didn't draw these other circles in here. There is another circle here. And what was that circle? Near the southern tip of the globe. A little circle near the South Pole. Not super near, but close. There's one up here also. There's one up here called. What's that?
Polaris.
Okay, Polaris is the North Star. It's always over there somewhere. But what is a circle here around the top or bottom of the globe? Okay. It's this little dotted line here, and that little dotted line here. That's the Arctic Circle and the Antarctic Circle. Okay? Now what's significant about them? And when is that significant?
North and south.
Those are very far north, Arctic Circle, and very far south. So this would be the Arctic Circle here, Arctic Circle here, Antarctic Circle down here, Antarctic Circle around the South Pole here. What's significant about that as far as our, what's happening then at the solstices, when the sun stands still, as low as it can go, as high as it will go. What's happening in the Arctic and Antarctic circles there? Over here in the Arctic Circle, 24 hours of darkness. Down here, 24 hours of daylight. Up here, 24 hours of daylight. Down here, 24 hours of darkness. Right, that's what those circles represent. Okay? So again, winter solstice is greatly exaggerated on distances from the sun. Summer solstice, autumnal equinox, spring equinox, or another term, vernal equinox. Okay? Now I get the term vernal, I think of that as being green. There is green in French. Okay? Now, let's move on to rotation and the Earth's axis. Okay? Now, before we get there, there are a couple of these examples. Let's just take a look. What is the latitude of an observer who measures the sun's altitude of 38.5 above the southern horizon at noon on the summer solstice? Okay, really you have to draw your little pictures, and we've done that in lab. Let's just leave that one, okay? Now, it says there's a concept applied. Make a chart to show the time of sunrise and sunset for each month. For a month. Calculate the average daylight and darkness. We sort of did that in the last lab, so I guess we'll leave that one alone too. So let's move on to rotation. Okay? Now, the Earth rotation axis is tilted at 23.5 degrees. That's what defines all the things we've been talking about almost. This accounts for the seasons. That tilt of the Earth's surface as we go around the sun. Right now we're right about, let's see, wrong way. We're right about here, aren't we? Yeah. Yeah. There's still longer days and shorter nights. And on September 21st, September 21st will be right here. So we're right here, okay? Right here, right about now. Yeah. Okay. We're somewhere around there now. Determined by the orientation of the rotation axis, the winter solstice is when we're pointed away from the sun, okay? When the sun goes as low as it will possibly go in the sky and stops in and starts going back up. So solstice means sun is still. It doesn't move that day. It's dropping, less and less and less, stops, and then starts increasing again. Summer solstice the other way. It's on the other side, and the sun is rising higher each day until it stops and then comes down. So the sun stands still. Summer solstice. Spring equinox, 12 and 12 and 12 and 12. Okay, everything is 12. Daylight darkness. That's when the sun is directly over the equator, and autumn equinox directly over the equator. Now, what is the celestial equator? Why are they bringing that back up? It's a line on the celestial sphere above the Earth's equator. We have talked about that from almost day one. So, why are they bringing it up here? Well, if you extend that out, here's the Earth here at our 23.5 degree tilt, and the celestial equator on the celestial sphere is like this, and the ecliptic is here, because the sun's fairly flat. And our ecliptic, our equator is tilted at 23.5, and so is the celestial equator. All right, North Star is always directly overhead, so that's why we got it there. The spring equinox, or when the ecliptic crosses the celestial equator in the spring, and autumnal equinox is when it crosses it in the fall. Maximum deviation here, sun above the celestial equator in the summer, below the celestial equator in the winter solstice. All right. Any questions on that? Stuff we've been talking about all three chapters. Does the Earth really rotate? Those members. Sorry. I think I've heard some of you refer to some friends who were in the Flat Earth Society, maybe. Those members of the Flat Earth Society, of course, the Earth is not rotating. The sun is moving above us, and the stars and everything else. We know that's not true. Okay. But what evidence do we have that it really is rotating? Okay? Say again?
Didn't they say, like, didn't they, I don't know, it was something.
Don't worry.
Let me see.
What did it have to do with?
It with like finding out, I guess, trying to see how, or as far as the earth rotating, how they figured it out.
Okay. Now how they figured it out, there's several ways, but one of the earliest pieces of evidence, and this was something that I know Galileo did, and perhaps people before him, because Galileo, remember, perfected that early telescope. And when he perfected it, he was then able to look and see Jupiter. And Jupiter has that characteristic red spot, and he could see that from one day to the next, the red spot was moving. So he knew that Jupiter rotated. Well, Jupiter's rotating, and guess what? You don't ever look at the sun to see this, but they can detect these things. On the sun, they have these things called sunspots, and they can see the sunspots are moving. So if the sun's rotating, if Jupiter's rotating, why wouldn't you expect the Earth to rotate? So there's one piece of evidence. All the other celestial bodies are seen rotating, especially Jupiter and the sun. But there's another. Have any of you been to McLean Science Center? Okay. Off, sort of in one corner, there was this great, big, long pendulum. Was it there when you were there? That went back and forth like that. Okay. It's called the Foucault pendulum. Okay. It may not be there anymore. The last time I was there, I don't remember if I saw it, but I know early times I always went by to look at it. But in France, I think in the Marie and Pierre Curie Center or somewhere there, they have this huge pendulum. And if you were to watch it, it just goes back and forth. But if you were to watch it over the day, I'm doing speed up big time, it does like this. And it is changing ever so slightly. In 24 hours, it does all the way. The Foucault pendulum is a pendulum that oscillates in a fixed direction, but it changes as the Earth rotates. Okay? Now, so there's a very definite thing. Now, here is a way you can kind of illustrate this. If we had a revolving stool, and we could get one, and had a thing like this with a ball on it, and turn the stool slowly, you would see that ball does this. Well, that's what the Foucault pendulum is doing as the Earth is spinning. Okay? It actually is changing direction. And that describes that the Earth must be spinning too. And here's the third. Yes? Is it time?
What is that?
Oh.
The one called just like that. It's a pendulum. But
Yeah.
What is the other one called?
It's got the balls that are three in the middle, and then one smacks, and the other one comes out.
Is that what you're talking about?
Yes.
Yeah. That's called I'm bored game. Okay. Okay. People have on the desk. Yeah. That.
Does it have at least a little bit of something to do with physical science?
Oh yeah. I mean, it has to do. It illustrates momentum and conservation of energy and a lot of things like that. In the physics, if you take Physics Science 112, we will actually do kind of an experiment, not with that, but with something like that. Okay. It doesn't have to be a pendulum, though that usually is. But that just illustrates basically conservation of momentum and conservation of energy. Okay. But this is the Foucault pendulum, which illustrates this. Now, the third effect that people have noticed is called the Coriolis effect. It's the deflection of paths as the Earth is rotating beneath a moving object. So if something were to come from way outer space and the Earth is turning like that, as it's coming closer, it seems like it's deviating. If you're on the surface of the Earth, it seems like it's doing that, but it's falling straight. It's just that the Earth's spinning underneath it. Okay? So the Earth is rotating beneath those objects. Now, the Coriolis effect is the result of the Earth spinning and the downward motion, and that's what creates, what kind of watch are we on now? Tornado. That's what causes a tornado. Because what a tornado is a place where there's a very low pressure. Okay? Very low pressure, that means the air is rushing down toward the Earth, but with the Earth spinning, that creates a twisting motion of the air. Another thing this creates, have you ever pulled the plug in the bathtub?
No.
And what happens? Yes, it doesn't go straight down. If you were sitting right on the equator, you pull the plug, the water just does like this. The further you are north or south of the equator, the more spin you get in it.
That's how whirlpools.
Yes, whirlpool type thing. Yes, exactly. Okay? Hurricanes all spin in the same direction in the northern hemisphere, but in the opposite direction in the southern hemisphere. In fact, low pressure systems spin. Yes.
So what you're saying is, the further distance you are, whether north or south, the twistier, I guess?
Well, yeah, the greater the effect of the Coriolis effect, exactly. Now, I had a physics, this is again showing how crazy physicists are, weird or something that they are. I had this physics professor. He was pretty high in his field. He was a crystallographer, and he was like the editor of the main crystallography journal in the U.S. Or international. It was the International Crystallography Journal. He was one of the main editors. He was really pretty far up there. Pretty good professor too. I had him for 2 or 3 classes, very different classes. And boy, when you got him in something that had to do with crystallography, he was way up there. Regular old physics classes, he brought down, but boy, when he was dealing with that. And because of this organization, the International Crystallography Society, or whatever it was called, was going to have a meeting in Rio de Janeiro. Anyone know what that is?
Brazil.
Say again?
Brazil?
In Brazil, exactly. Now, it's not the largest city in Brazil. That's Sao Paulo, which is really not too far away there. Sao Paulo is there. Rio is there. Sao Paulo is the business capital. Pretty serious people there. Okay? Making a lot of money and stuff. Rio, on the other hand, is the party capital of Brazil. Have you heard that before? Yeah, that's a party city, all right. So they had the International Crystallography Society meetings in Rio de Janeiro, okay, Brazil. And, of course, being main editor of the journal, of course, he was needing to attend to that, so he got to travel to Rio, okay? And he was so excited when he got there. He just could not wait. For what? To run into his hotel room and flush the toilet. Because he wanted to see if really the water went down the other way. And it did. That's what makes physicists excited. Duh. Okay. In the party city of the southern hemisphere. He did. That's Coriolis effect. Okay. Things rotate differently north and south. So a high pressure area that rotates clockwise in the north, high pressure rotate counterclockwise in the south. Low pressure areas like tornadoes that rotate counterclockwise in the north, they rotate clockwise in the southern hemisphere. So that's the Coriolis effect. Also, I don't guess any of you probably are ever going to be dropping bombs on anybody from aircraft, but you have to calculate that into it because you drop the bomb, the earth is turning, it does have a effect where it's going to land. You have to count all that in their calculations. Unless you have smart bombs that follow some sort of a track somewhere, then maybe you don't have to worry about it. Okay. Another one of the motions Okay? They do have a picture in the book. It's a drawing or a lithograph or something of Fouquet doing his pendulum, great big old tall, from a long way away, but it doesn't indicate where this is. It seems like it's the Pasteur Institute or one of those fancy institutes in France. But another motion, and this is a very slow motion. That's what we call precession. It's the very, very, very slow wobble of the Earth's rotation axis. Now, we said our angle is now 23.5 degrees, and it is approximately, but it may not always be the same 23.5 degrees. If it's 23.5 degrees now, but if it's doing this kind of stuff, it may stay 23.5 degrees, but it may be pointing in a different direction, okay? The reaction of the Earth to the gravitational pull on its equatorial bulge by both the moon and the sun tends to twist us a little bit. Now, when I say very slow, 26,000 years for it to make its route around there once, okay? We're not going to notice it during our lifetime at all, okay? 26,000 years? Yeah. Okay. The changes of direction of rotation are on the celestial sphere. The Polaris has not always been our North Star. Yes?
How exactly do you know that it takes 26,000 years?
They have,
precision? Like, obviously they haven't lived that long.
Right. They measure the small amounts of changes now and project them into the future and past. Okay? And in fact, here's a couple things. Polaris has not always been our North Star. There's been a few times when there's really no star directly over the North Pole, like there never is in the South Pole. You never see a star over that because it's a big blank part of space down there. But Vega, remember we ran into Vega in our first lab. At one time, I'm pretty sure that was the one that was our North Star. It's a much brighter star than our current, but yeah, it's not during our lifetime. But another thing, and this we have noticed, I don't know if any of you follow Zodiac or read that or the horoscopes and stuff, but those each represent constellations that basically line up along the ecliptic, okay? Different months of the year or periods of the year. It doesn't cover an exact month, but a couple of them aren't on the ecliptic anymore because we have tilted a little bit. Back when they were first named, they were sitting right on it, but because our tilt has changed a little in the orientation, a couple of them have gotten off, and there's actually other constellations that are better, but we don't change them because everybody follows those. Yes?
There are like zodiac signs.
No, they keep the old ones, but they're not the ones on the ecliptic anymore. Something else is on the ecliptic now. I mean, it's all, I'm sorry to say hocus pocus anyway, but so it doesn't matter, but we still call them by the old names, even though some of them aren't quite on the ecliptic anymore because very slowly we're changing. What's that?
Do you know which one?
I've read or heard it, but I don't recall which one it was. It may actually be in the book. Let's see. No, all it says. They say in about 12,000 years, the star Vega will be above our North Pole, not Polaris. I don't think I'll be around to see that, okay? So, not going to be a big deal with me. No, they don't say which one of these. It just says the moving pole causes changes over time, which particular constellations are hidden by the sun on which specific date, meaning the zodiacal date. So, I don't know. Remember, some of them were real close to each other when we did that lab. This was either this one or that one, because we didn't have our measurements right because it looked like it was right in between. And it's the kind of thing. They're right adjacent to each other. So it's not a major change, and it certainly happens very, very slowly. Okay? Not noticeable at all. Within a lifetime. It has to be over generations, over millennia, before you can really tell the difference. All right. It's a lot like a top spinning. If you ever played with a top, most people don't know what this is anymore. You do a top, if it's going really fast, it almost stands directly up. But as it slows a little bit, you'll see it starts doing that. Well, the Earth isn't necessarily slowing, but we are precessing. It's spinning like crazy, but precessing very, very slowly. That's what we mean by precession. Okay. If this is the North Star now, sometime later it's going to be Vega. But that's about 12,000 years from now, so we won't see it. So that's changing like this so slowly. There's no perceptible thing until you look back over literally centuries and millennia. Yeah.
I thought the Earth was completely round. How can it wobble or precess like a top if it's completely round?
Okay. Well, a top is very symmetric around, and yet it precesses. Okay. Now that was a great explanation of it. But number one, we're not perfectly round. Remember, we're a little fatter around the middle and shallower here. It's that equatorial bulge and because we're tilted away from the sun and the moon is tilted away from us, then the sun and the moon pull a little bit more on that bulge than they do on this. So that's what makes us wobble a little bit. Okay? That's at least their description here. That gravitational pull on both the sun and the moon by that equatorial bulge. That's what makes us do. Because we're not perfectly round. We're not a perfect sphere. We're an oblate spheroid. Okay? Fat in the middle. Unfortunately, I can relate. Okay. All right. So this is showing an extreme of that. Now, yeah, okay, that makes sense. The North Star today is our pole star, but then sometime later, very slowly, about 12,000 years from now, Vega will be the North Star. We'll slowly, very slowly, have precessed around until Vega's our pole star. Right now, and throughout most of history, it's been the same. Okay. Kedrick, right? Okay. Anyone else come in since I called roll? Okay. So, our North Star is called Polaris now. They really need to get a different name for it then because it won't be the Pole Star, it won't be the North Star. But, you know, it's a little dim little star anyway, so who cares what it's called once it's no longer our pole star. Vega, no, that's a bright, bright star. Okay. But I won't be around to see that. All right, now we're moving to 16.3, which is place and time. Okay? Earth's periodic motions provide a basis for determining the place and time. Now, I have trouble really rationalizing the motion determining the place. It does, sort of, okay? The fact that the Earth spins around an axis, okay? That axis is what helps us determine a place. Because that gives us two fixed points. Okay? Two fixed points on the globe. That gives us yet another fixed point thing. If you go equal distance from the axes, what are you mapping? What's equal distance from these two axes? equator, equidistant from the equator. They're equal distance from the North and South Pole. So that provides a basic. So to me, that's not a motion, though it's a result of a motion, that we have an axis. The axes provide the first reference for place. And those motions also give us references for time. So these are two completely different things, but they both are important. The rotation provides an axis, of rotation, useful for determining positions on the globe, locations on the globe. It gives us a reference to the equator, and then from the equator we can measure back out to the poles, and we can measure 0 degrees, 10 degrees, 20 degrees, up to 90 degrees, or south, do the same thing. So that provides us at least one of the defining criteria for where you are. Now, the rotation and the revolution determine cycles which can be used for time standards. What is one spin around the Earth? 1 day. What's one revolution around the Earth?
A year.
Of the Earth around the Sun? That's a year. So you see the combination of the rotation and the revolution, that gives us days and years. And I asked this question before. What are those 12 not quite equal periods of time in a year? Months. And what determines them?
Days.
Say again. Why do we have the months where they are? M-O-N, month. Put an extra O in there. You get it. The moon. The moon's the thing that then, so one complete cycle of the moon is approximately 1 month. Approximately, not exact. Okay? Actually, one rotation around the sun is not exactly 365 days either, is it? What do we do every 4 years?
Year.
Have a leap year, because it's not exact.
Well, we got 30 days and 31 days.
Okay. I do not know who came up with that. Okay. Why do we have I can understand some 30 and some 31 because it doesn't come out an even number of days. But why do we have a 28 thrown in there? I mean, that makes no sense at all. But they did it. Whoever they is, they did it. Okay. So this helped determine times. Now, the combination of going around the sun and the fact that we have a tilt gives us another way to divide up the year into 4 seasons. And those 4 seasons are marked by what 4 events? The summer and winter solstices and the fall and spring equinox. That's what determines those 4 seasons. Okay, exactly. And those all have to do with what the Earth's doing. Going around the sun with our tilt. That's what makes that happen. So let's talk about place. If we were a member of the Flat Earth Society, and really were, all we'd have to do was give how many north, how much south, we'd have a peg, right? How many units north or south of a fixed position we are? That would give us our Y values. How far east or west we were around that fixed position, that would be an X value. It would be really simple if we were on a flat surface. We're not, okay? And then the intersection of 2 straight lines, that would ping us right where we are. However, we are not a perfect sphere, but an oblate spheroid, so therefore, straight lines don't work as well when you live on a curve, right? Okay, so that does give us some problems there, okay? Doesn't quite work so well when we're on a curved surface. So what we have to come up with is another way to measure things. So here, if we're on a flat right, all we need was an X coordinate and a Y coordinate. We've got it not. We're on a sphere. We need different coordinates from that. And the first of these is what we call, and they have 2 names. Some people call them the parallels. Others call them latitude lines. I like to call them latitude. They are parallel because every slice is parallel to the previous slice, okay? But this measures how far north or south you are from the equator from an angle's point of view. So just imagine you cut the Earth exactly into this way and to that way and pulled out that quadrant that you had there. Then if you put a protractor, in fact, let's cut away half of it. Put a protractor there, how many degrees north up to 90 you are, that gives you your latitude. And these are measured by the parallels. And you see here are the lines. There's the equator. I believe these are 15, 15, 30, 45, 60, 75, and 90. So those are evenly spaced and going south as well. 15 south, 30 south, 45 south, 60 south, 75 south, and 90 on the south pole. Okay? That's given to us by the axis and the equator, which is the distance from the axis. Then you measure up or down from there. How many degrees? That gives you your latitude. Those lines are sometimes called parallels. Okay, and those are pretty easy to measure. I mean, pretty simple concept there. Okay, here's that cutaway view I was talking about. And if you had placed a protractor with the center right in the center of the Earth, of course it'd be melted by then, and measure the angles up, it would be 20 degrees north, 40 degrees north, 60 degrees north. You skip 80 and now it's straight to 90. Okay? The globe did 15, 30, 45, 60, and 75. Okay? They did every 15. Makes a little more sense, but it probably was harder to draw. Okay? Now, that gives us one dimension, north or south of the equator. We need something else telling us how far east or west we are from something. Well, the equator is real easy. You can always locate the equator anywhere by the equidistance from the north and south poles. That's the equator. Okay? I'm not a Florida State or Florida fan. No, that's not what I was doing. Okay. East-west is a little tougher. Okay? What they do, they take... Now, by the way, let me give you this other term. The equator is the only one of the parallels that we call a great circle. A great circle actually passes directly through the center of the Earth. If you were to cut right here, right in the center of that circle would be the center of the Earth. If you cut right here, you're not at the center of the Earth. You're above the center of the Earth. And down here, you'd be below the center of the Earth. That's the only one of our parallels that is a great circle. It goes right through the center of the Earth. Now, you have lots of great circles this way. Here's one. Here's one. Here's one. Every one of these cuts right through. See, the thing about parallels, they're about the same distance apart going up. That's why they call them parallels. When you talk about these that go east-west, they're this far apart here, but as you get closer to the poles, they're almost touching, right? Because all of those are going through the center of the Earth. And that's what we call our longitude lines, okay? Now, they also are called meridians, okay? Remember our celestial meridian. From due north, straight overhead, to due south, that's our meridian. If you extended that through the Earth, it would go right through the center of the Earth. Somewhere over in Mississippi, they have a little bit different one. In Georgia, we have a little bit different one. But near the North Pole, they all come to a point there, okay? And South Pole as well. So these are the way we measure this. So every one of those is called a meridian, or a longitude line. Well, it's easy to know. You start the latitude from the equator. 0, plus or minus, going to 90 degrees. Where do you start something that goes around the circle? Where's the starting point? What did they choose? They chose one and called it the prime, meaning the first, the major, the first, it means prime, premier is prime meridian. And because this was probably determined back when Britain was queen of the oceans, they chose the Naval Observatory at Greenwich, England, to be, that's where the prime meridian goes through. So you do a point from the North Pole to the South Pole that goes through Greenwich, England, okay? And that's it right there. It's called the prime meridian, okay? And it's called, by the way, they call it Greenwich Mean Time. That's the one that's centered there. I don't know if any of you remember that old, now it's old, I thought it was new at the time, TV show. It was called JAG. Remember, it's the Judge Advocate Corps, okay? Huh?
I've never seen it, but
You remember? Okay. On that, every episode, every now and then, they just and type at the bottom something or another Zulu. That's how they kept up with time. Well, Zulu means Greenwich Mean Time. And actually in the military, or at least in the Navy, I think it is other places, you measure everything by Greenwich Mean Time. Because when we were on a ship, crossing time zones going across the Pacific, your time was changing every few days because you crossed another time zone. But if you referred to everything as Greenwich Mean Time, you had something that was fixed and never changed. I'm getting ahead of myself there. But anyway, that was it. So you pick the prime meridian, and then you can go east, and they usually do these, they're showing 30 degrees. 30 degrees, 60 degrees, 90 degrees, that's not right. Okay, this doesn't look right anyway. Looks like maybe they're doing 15, 15, 30, 45, 60, look right either. Whatever they're doing, but you go halfway around, you get to 90, I mean, a quarter of the way around, you get to 90, halfway around, you get to 180. Stop there, and then going the other way, you're going west. 10 degrees, 20 degrees, 30 degrees, all the way around, so you get 180 degrees west. Okay, from the prime meridian that goes through Greenwich, England, we're on the western side of that. Yugoslavia, Egypt is on the eastern side of that. Okay? Until you get all the way around, and then you're 180 degrees. That's the other side of the prime meridian. It has a name too, but we're not going to call that name yet. Okay? Just to keep it from getting confusing. So that's how we do. So latitude goes from the equator, north or south, 90 plus 90 minus 90. You're 90 north, 90 south. Longitude lines go from the prime meridian east and west to 180 degrees, all the way back again. This time you put your protractor down like this, and you go up to 90 and then around to 180. East or west. All right. Now, how then do we determine your position on the surface of the earth? Just like every point on the board, you can measure some on a flat surface, some units to the right or left of the origin, up or down from the origin. That determines where you are. Position on the earth will then be the intersection of parallels, your latitude lines, with the meridians, which are your longitude lines. They define, with respect to the rotational axis of the earth. Everything is reference to that. So the parallels measure the latitude, north or south of the equator. The meridians measure longitude, east or west of the prime meridian. These go north or south, plus, north 90 to south 90. These go east 180 to west 180. Every point on the globe can then be uniquely defined by one particular parallel and one particular meridian or longitude line. Okay? Now this is a picture we've sort of seen before. They've shown it again. These are the parallels going north or south. This is showing north of the equator. And we've seen that one before too. How you would measure those. Imagine you had a protractor at the center of the earth. measured north or south, so many degrees up to 90 degrees. Whereas the longitude lines are so many degrees east of prime meridian or so many degrees west of prime meridian, and those go plus 180 east to 180 west. There they meet on the same meridian again. And this is how you picture that. Lay your protractor flat, and it goes 0 to 180 degrees. Okay. Now, others, and we've already mentioned these, every one of them today. Special parallels, these are the horizontal measures, the latitude lines. Special parallel, you got to go? Okay. Just get one. Okay. And I think if you listen to the YouTube, have you been able to get on YouTube yet?
Not yet.
Okay. Hopefully I have the link there, but if I don't, you can still find it on YouTube. Just look for Physical Science 111, this class, a recent one, today's one, in fact. Okay. Yeah. All right. Certain of these parallels are climate related. Someone named some of them that could be. Tropic of Capricorn, where is that?
South.
How far?
23
and a half.
Yeah,
Minus 23 and a half, or south 23 and a half degrees latitude. Another one. Tropic of Cancer is north 23 and a half degrees. Arctic Circle. Now that one is 23 and a half degrees from 90 degrees. So subtract 23 and a half from 8960, or 2330 from 8960, and you would have, goodness, brain's not working. Yeah, 6630, right? I think it is. 6630 north, 6630 south. That would be Antarctic Circle. Okay? One more, you sort of left out the obvious one.
Arctic.
Yeah, Arctic is 66 and a half north. What did you start from? The equator is 0 degrees. Okay? Now, why do they call those climate related? Because the sun is always directly overhead, somewhere in between the Tropic of Capricorn and the Tropic of Cancer. Every day of the year, when you go around here, the sun's directly overhead. It's directly overhead Tropic of Cancer on June 21st or 2nd, whenever that is, the summer solstice. Is directly overhead at Tropic of Capricorn on the winter solstice, okay, near the 21st or so of December. And it's directly overhead the equator when? Halfway between all the winter. Yeah, March 21st and September 21st or so. And those are the equinox. Yes. That would be when it would be directly over the equator. But every day in between is either going up or coming down, going up or coming down, directly overhead in the tropic. Because it's directly overhead, you get more direct solar radiation. Those are the warmest part of the globe in general. Okay? Go up to the very northern one, the Arctic Circle and the Antarctic Circle. Above those, or on either side of those, you're the very coldest part of the planet, generally. Because then, at least for some period of time, the sun never sets. When we're in our summer solstice in Antarctic, which is their winter solstice, the sun never sets anywhere inside outside the Antarctic Circle. It never rises there, never sets up here on the solstice day. And on the other solstice day, it never sets here and never rises there. It comes close to setting, but skims the horizon, but never dips. Okay? Then the other part the big band here and here, these are called the temperate. These are called the tropics, the frigid, Arctic environments. These are called the temperate. In between. Not as hot as the equatorial region in general, but not as cold as the Arctic regions in general. Okay? So, not only is time and place determined by this, climate is determined by this, your localized climate. All right, so let's move back to time. We've already mentioned some of this. Okay, it's now, what, 2:30 approximately, right? We'll go to 3:15, okay. The time standards depend on measuring intervals between evenly spaced periodic events. Okay? So astronomical examples include the rotation of the Earth on its axis. How long does that take? One rotation, one spin around their axis? 1 day, 24 hours approximately. Okay? Revolution of the Earth around the Sun? About 365, not exact, days in the year. So there we have our astronomical example for the day, spin of the Earth, the year, revolution of the Earth around the Sun, the season between the equinox and solstice and equinox and solstice, equinox. Those are our seasons. The month, moon. That's based on the phases of the moon. One complete phase of the moon is approximately a month. I'll leave it approximately. Okay. Now, guess what, team? There's not one and only one way to measure a day. Okay? We're used to looking at our clocks and saying 24 hours is a day. Well, it depends on what kind of day you're talking about. Okay? If you're basing your day on our sun, then that's one thing. And then we do it from noon one day to noon the next day. Why we choose noon? That's the highest the sun will ever be on that day. Okay? But if you were doing this at night and you picked out a star over here and the highest it's going to be, don't pick the North Star. Okay? It's always the same. But pick some star that's moving around. What's the highest point it's going to reach day to day? You're going to get a different thing from the sun. And here's why. Well, we'll get to that. I'm getting ahead. Okay, but that's what it means, different ways to measure days, months, and years. One is based on the sun, one's based on the stars. Okay? Now, for some reason, they use different terms for them. Okay? All of them deal with solars. The solar day is based on the sun, the solar month is based on the sun, the solar year is based on the sun. However, we call them different things for the based on the stars. One's called, just had it in my brain and now it's formed to sidereal, if we're talking about a day. We call it tropical. Why tropical? If we're talking about a month. And I don't remember what the special name for a year. I guess that's regular year and leap years. I guess that's what they mean there. Okay, so let's look at daily time. Okay, that's not exactly what we mean by the daily show, but it's close. Okay, not really. Okay. The Earth-Moon motion. That's what determines daily time. Now, if you were to look at that Earth-Moon motion from the North Pole, the Earth revolves counterclockwise. If you're looking at it that way, the Earth is going like this. Okay? If you're above it looking at it, the Earth is spinning counterclockwise. Okay? I'm sorry. Rotating counterclockwise. Revolving around the sun, also counterclockwise. If you're looking from above, we're moving the opposite direction the clock would move, counterclockwise. And we rotate the same way. Would Venus be the same? No, Venus is rotating around the sun, or revolving around the sun counterclockwise, but it's spinning on its axis clockwise. Ew, Venus is weird, but awfully slowly, by the way. How about Uranus? Uranus is going counterclockwise around the sun, but it's sitting something like this as it's spinning. I mean, really strange. If anything lived there, it would be totally confused. Nothing lives there, so don't worry about it. All right. But on Earth, that's what we're doing.
Yeah, question.
Yes.
So you know when they send people to the moon and all?
Say this again.
You know when we send people to the moon?
Yeah.
Alright, so you know, the moon doesn't move, right? It doesn't spin.
It spins one time a rotation.
So when you're standing on the moon and you're looking at Earth, you're rotating while the Earth's rotating?
No, you're rotating while you're moving around. It's a weird thing about the moon.
The basis point I just wanted to get was like, so if you're on the moon, could you literally just watch the Earth spin?
Yeah, you can. It'll be so slowly you might not pick it up, but it's a pretty slow process. The moon, if you were on the moon and facing the Earth, you'll never lose sight of the Earth. If you're on the moon and not seeing the Earth, you'll never see the Earth, because it goes like this. One face is always facing the Earth, always. The backside never faces the Earth, okay? But if you think about it, that means it has to spin on its axis one time for every time around, so it can keep that orientation. So in a sense, if you thought of the Earth as being its sun, its day would be its year, okay? But we don't think of things like this. No one lives there to measure it. So it's sort of a bizarre thing. Okay. Now, on Earth, the sun rises in the east and sets in the west, or at least approximately so. Okay. In the summertime, it will be north of east. In the wintertime, it will be south of east. Also setting north of west in the summer and south of west in the winter. Okay, so it's not exactly east-west, but pretty close. All right, now here is why we have two different days. One spin around the Earth, you would think would be one day, right? Okay. You want me to sun for us again? Okay. So here is the Earth spinning like this. Okay. Now, if the Earth was just sitting here, one spin would be exactly one day. But if we're measuring a day by the sun, while we're spinning like this, we're also moving like this. Not very much, but a little bit. So therefore, we move just a little bit. We have to spin a little bit further for the sun to be directly overhead. See, sun directly overhead right now. Okay? Now, when I turn one complete time around, we're here. For the sun to be directly over here, I have to go like this, because I've moved in this direction. So I have to spin a little bit further. Now, if we were measuring by the stars, let's say there's a star back here that we're measuring by. Stars are so far away, one time around that star is exactly where it was. We're not moving around the stars, they're fixed. We're moving around the sun so it doesn't look like it's fixed. That's the bizarre thing. So we're spinning here. One complete spin of the Earth. Now this is looking, if we're looking straight down the North Pole here, one completely spin of the Earth would be here. But the sun would be directly overhead at this time. Now it's not. We have to spin just a little bit more to get the sun directly overhead. Or as close to it as it's going to get. So this is what defines a solar day. A little bit longer than a sidereal day, which would be based on the star. Some star out here, directly overhead here, be directly overhead there. So far away is parallel. Okay? That would be a sidereal day. A little bit longer, that would be a solar day. Okay. What's that?
Go back one.
Oh, I'm sorry.
Okay, we're good.
Okay, everybody good? All right. So, what is noon? Noon for us is this time at which the sun is crossing our celestial meridian. That's the highest it's going to go that, any day. Now we call that, or the book calls it, apparent local noon. Okay? That's at every meridian, every particular longitude. It has a time when it's exactly overhead when it crosses that meridian. Okay. Now, when I was in the Navy, we had to shoot the stars, but we also shot the sun, you might say. We tried to find at exactly noon, we determined what was the elevation of the sun, because that determined where you were east-west. North Star, at night, that tells you how far you are north, because the North Star is, the angle of the North Star is exactly your latitude, wherever you are in the ocean. Angle of the North Star gives you your latitude. Of course, if you're in the southern hemisphere, you can't see the North Star, okay? But in the northern hemisphere, which is where we were most of the time, you could see the North Star. That gave you that, our latitude. Well, your apparent local noon, only we called it local apparent noon, LAN. That was a lot easier to abbreviate. This would be ALN, which I don't know what that would be, but LAN, land, local apparent noon. That would give you specifically where you were longitude-wise, okay? And the apparent local solar time is given by the position of the sun in the sky. Now, the earliest clock were the sundials. Now, another name for that is a gnomon. I think the G is silent, gnomon, okay? Rather straight. I think of that as being these little, ugly little creatures, but it's a different thing, okay? That's a gnomon. And that is not the time that shown on clocks. The reason for that is we do all these strange motions, okay? Our tilt, getting further and closer to the sun, all that affects that, okay? Whereas the sundial gives us approximately what it would be that day. So, mean solar time is the time average from the apparent solar time. So if you did the average day throughout the year, that gives you your mean solar time. Now that's averaged over two effects. Okay? Now remember we said that July, or first week in July, we're the closest we ever are to the sun. No, set it back. Farthest we ever are to the sun. On the the first week of January, we're as close to the sun as we're ever going to be. Okay? Because we're changing our distance to the sun, ever so slightly, but still changing the distance to the sun, that affects us a little bit, but here's the other way it does. When we're closer to the sun, we're going faster. When we're further from the sun, we're not going quite as fast. Okay? That comes from Kepler's second law, I believe. Huh?
I was going to say the third law, but I wasn't.
The third law does the relationship between the period and the what was the second thing? Period and the so in some ways it does relate to that too, but it's more the arc that's cut out, and that's the second law. Okay. So, but both of those relate to it in some way. All right. So, because we are different distances from the sun, it changes our orbital speed ever so slightly. Remember, we're not a lot difference in that elliptic orbit from a circular, but it is a little bit. The other reason is that we're inclined to the ecliptic, so therefore that inclination makes a little bit of a change too of where we are, and how high the sun's going to be, how long it takes to get there, that kind of. So the mean solar day is 24-hour average from the mean solar time. We average all those up from noon to noon to noon to noon every day. Average those, you get about 24 hours. Pretty close to it anyway. Okay. So that's how we refer to a day. But two different ways. The length of time required for the Earth to rotate once on its axis, that's a sidereal day, because that would be star to star. I mean, one star to the next day when it reaches maximum height. The intervals between two consecutive crossings of a celestial meridian by a particular star. Now, little variation here because our rotational rate is pretty close to constant. It's the revolution that is not constant. Okay. The apparent solar day, okay, interval between two consecutive crossings of the celestial meridian by the sun, not by a star, now is influenced not only by our spin of the Earth, but how fast we are moving around the sun. That's what changes that every now and then. So the solar day is about 4 minutes longer than a sidereal day. This is the sidereal day. The solar day is about 24 hours. The sidereal day is 23 hours, 56 minutes, and 4 seconds, to be fairly close. Okay. Why they put this here, this is under solar, this should be over here. Because the solar day is about 4 minutes longer than this, which would make it right at 24. And notice they say about 4 minutes. Sorry, that's in the wrong place. So in your notes, be sure you put that under sidereal day, not solar day. Solar day is 4 minutes longer than that, which puts it right at 24. And I'm coming back to it, but you'll notice on the slide, mean solar day is 24-hour average. So that has to be the sidereal day, which is 4 minutes shorter than the solar day. Does that make sense? Yes.
What's the thing about the sidereal day again? It's longer than...
That's based on the star. Sidereal means based on stars. I think that's what it means anyway. That's effectively what it is.
And it's longer than...
It's one complete revolution of the sun, a revolution of the Earth. But notice we got to do another 4 minutes to get back to facing the sun again, because we're going around the sun. So that's the sidereal day, which would be, if we based our days on the stars rather than the sun, that would be it. But since the sun governs just about everything, let's not do that. Okay. Basically, at the end of a year, you'd have to add another day then. So that's what it comes out being about. Sidereal, let's see how to say this. A solar day is about 1 day longer a year than the sidereal. Takes one more sidereal day to make its way around the sun than a solar day, because you see we've spun one more time going around the sun. Okay, everybody got it? All right. Now, this introduces the thing we call the equation of time. Okay? Now, sometimes this equation of time is actually called, well, it has a couple of different names for it. And let me see, I can't remember if this edition names it or not. And by the way, the little example 16.3 is what I was just talking about. How many sidereal days are in 1 year? About 366 sidereal days, not 365. And then it's asking what is the age of a 20-year-old person measured in solar days and what it would be in sidereal days. You can work that out. It shows you how to do it in the text. I don't know if you're particularly interested in that. Okay. Now, this equation of time. It uses a verb here, traces the yearly variation between apparent local time and mean solar time. Now let me give you an approximate way to do this. Now, you have to use your imagination here. Let's just say, right here we're facing, due north is that way, this window is pretty much on the southern side of the building, right? Okay. Now, if that tree weren't there, maybe a couple of other trees weren't there, and we were to cover that window completely, black it out. This window too, we're going to completely black out, except we're going to leave one little hole somewhere about the middle of one of the panes of glass, one little bitty hole for light to come through. We're going to keep the lights off it and watch that beam of light come through, and at exactly the local apparent local noon, right that time, every day, we're going to make a little spot on the floor where that light comes in. At high noon, when the sun crosses our local meridian, and it's right there at noon every day, not time noon, but real noon, then we'll make a little spot on the floor. If we were to do that, we would map out something that looks like a figure 8 on the floor. Okay? You'd have to do it every day of the year, and this isn't showing it. Okay? Okay, it's not showing it. It's in your book. Actually, this figure, if you took this and folded it right there on top, then that would be your figure 8. Fat here, thin here. Okay? That would be the figure 8. Okay? In your book, you see it a little bit better. Okay? All right. On page 418, you see that. Now, I'm trying to see if they name it here. They call it the equation of time, but they do not name it here. We will name it in the lab today. Okay? So I'll go on and give it to you now. It should be in here, but it's not. It'll show up, in, believe it or not, in the next chapter. No. Maybe it was in the last chapter. I thought it was somewhere in here, but anyway. It's called the analemma. I know it's in the lab. We're going to talk about it in the lab today. Okay? The analemma. A-N-A-L-E-M-M-A. Analemma. It's also called the equation of time. I can't remember one, remember the other. Traces the yearly variations between apparent local time and mean solar time. If you were to do that experiment we just did, it would trace out a figure 8 on the floor. Two effects to it. The axis tilt, north and south, called different days of the year. In the summertime, the sun's going to be further up, and in the wintertime, it's going to be further down, so that's going to give a stretch to it that way, top to bottom. Okay? And then the orbital speed will give you east to west variation. If the Earth's moving faster or slower, then you'll get those variations east to west. And the equation of time is that cumulative plot of that entire figure 8 that you see in the text, and they don't give it in the slide set. In fact, my guess is it's supposed to be right there, but it didn't make it in here. Okay? I don't know why.
The definition of word analemma is on page 420.
420. Okay, I thought it was in this chapter. There it is, yeah. right? It's not a complete paragraph. The first partial paragraph at the left-hand column, there's a big figure on
Third
there.
line on the
Yeah.
420.
Yeah, it says the equation of time is often shown on globes, this one doesn't have one, as a figure 8 shape called the analemma, which can also be used to determine the latitude of direct solar radiation for any day of the year. Okay? Now, I do have another globe that's not as nice as this one. Pretty sure it does have an analemma on it. It doesn't. I just think it did. Okay. Now, so the axis tilt gives you the north-south motion of the sun, and the orbital speed gives you the deviation east and west. Now, don't think that you can bend this one over and get an analemma. You do get something that looks like a figure 8. That's just because the way they've drawn it here, this isn't any particular time or any particular anything else. This is just sort of showing where the sun would be at any time. This would be July 21st, December 30, July 21st, December 21st, March 21st, March 21st, September 21st, okay? Approximately, okay? That's just the ecliptic of the sun. Looks like it could yield the analemma, but it really doesn't, because it's not varying by speed. This one, though, you could. If you folded those over, you have basically your analemma. Right over this point, right here, and then bringing them together here. You see, this starts, where this begins, that one ends. So if you folded it over, the fat part would be here, the thinner part up here. That's the figure 8. Okay. The other name for that equation of time is the analemma. So, and we've already mentioned this before, but let's do it again. How far away, how many degrees is it around the equator? 360 degrees. How long does it take for the Earth to spin at one time? 24 hours. If you divide 360 by 24, you get 15 degrees. Every hour is represented by 15 degrees longitude. Okay? And that is what gives you your time zones. Now, do we use them exactly? No, we don't. We, what they call, adjust for local consistency. Okay? And that's what this map is going to show you here. Okay? The line here, these are just approximate. If you were to sort of do a straight line between here and there, you're going to come up pretty close to the Alabama-Georgia border, but not exact. But what they did, they kept all of Georgia on the eastern time zone and all of Alabama on the central time zone. With one little exception. This is, again, local exception. Anyone know anything about Phoenix City in Alabama? Okay? Right across the Chattahoochee River from Fort Benning, Georgia. Fort Benning is a big, major Army base. Lots of people work there. Some of those people would rather pay the lower tax rate that Alabama has than the higher tax rate that Georgia has. So a lot of them live on the Alabama side. Thank you, Georgia, for sending them over. But they work over in Fort Benning. So rather than unsetting and resetting their clock when they go back and forth across the Chattahoochee River, they set it for Fort Benning and stay on it. Now, I don't know if the whole city of Phoenix City does it, but there is a fair amount of the population that probably stays on Eastern Time. Okay? Poor old Tennessee is just that long state. It can't do that. If it tried to stay, then there would be the line, and it wouldn't be very smooth here. Okay? So Tennessee, basically Chattanooga and further east, Knoxville, they're on Eastern Time. Memphis and Nashville are on Central Time. So the state of Tennessee covers 2 time zones. Kentucky the same way. Okay? I don't know my positioning of the cities well enough to guess there. I'm pretty sure I think Louisville is somewhere up here. Must be on Eastern Time. And I just don't know about what's the capital of Kentucky.
Is it Louisville?
It's not Louisville.
Mulberry?
It's Lexington.
Okay.
Lexington, Kentucky, I think is the capital. It's somewhere right near there, so it's one side or the other of that. Now, here again we have Indiana. Indiana is mostly Eastern Time zone, but this portion of Indiana is really close to what city in Illinois? Chicago. So since, and this part of Michigan too. Since a lot of people here gravitate to Chicago for their jobs, then these parts are stayed on Central Time. Down here, I'm trying to think what the draw is. I guess it's just they had to cut somewhere because Indiana sort of sticks out over here. They cut off that and made it central. The rest of Indiana is eastern. Now, except for that little bit of Michigan there, Michigan's tried to stay all in the same time zone, including what they call UP. What's UP, Michigan? The Upper Peninsula. This part of Michigan is not directly connected to this part of Michigan. This is the Upper Peninsula here. Canada's up here. Lake Superior is right here. I believe that's Superior. Yeah, I'm pretty sure it is. No, that's Lake Michigan, isn't it? Lake Michigan is here. So it's completely cut off land-wise from the rest of Michigan. And that really should be in Central Time Zone, but to keep it on the same, they kept it there. Same thing down here. This little bit of Texas here is nowhere close to anywhere in Texas, any big city, but it's closer to Santa Fe, New Mexico. Since New Mexico is on Mountain Time, this part of Texas goes on Mountain Time too. Same thing here in Colorado. This part of Kansas is closer to the population centers of Colorado, so its state goes on Colorado time, not on the rest of Kansas time, Central Time zone. Nebraska just about cut in the middle, South Dakota sort of too, North Dakota almost the same. Poor Idaho, the northern half, most of the people there will gravitate toward Washington, Seattle, and this, the cities in Washington. The southern Idaho sort of gravitates more toward Wyoming, Salt Lake City. So as for Idaho, it's cut here, but even some of Oregon goes with Idaho here. So it's rather bizarre. That's what they mean local consistency. Florida, same deal. Florida is such a long state along the upper peninsula here, or upper panhandle here they call it. It stays with Alabama, whereas this part stays with Georgia. That's what they mean local consistency, adjusted for local consistency. Now, daylight savings time. I don't know what you feel about it. I'm not a big fan. Okay, the clocks are set ahead in the spring and then set back to regular time in the fall for an extra hour of sunlight during the summer evenings. To me, the reason for this is the bankers like to play golf in the afternoon in the summertime. Now, I've heard people say, no, it's the farmers. I don't think so. I know I grew up on a farm. I never cared for it much. But I know the dairy farm just just on the other side of us, just up the road from us. Guess what? Their cows needed milking the same time of day every day, whether they're on daylight saving or if went to daylight saving time, the milkers had to milk them an hour earlier, okay? Because the cows needed to be milked at that time. They didn't say, oh, wait, daylight saving time, we'll wait another hour. No, they needed to be milked then. So I don't think it's the farmers, but I've heard some people argue they're the ones that did it. I don't think so. Now, here's the problem, though. Let's start at Greenwich Mean Time. Okay? Give me a time of day, Greenwich Mean Time. Just make up one. 3 o'clock, Greenwich Mean Time.
AM or PM?
Second.
AM or PM?
PM, 3 p.m., Greenwich Mean Time. That means, okay, I need to get every 15 degrees, okay? 3 p.m. Greenwich Mean Time. That means here it'd be 4 p.m., right? Yeah. There it'd be 5 p.m. and this is, and what day? What day is it, by the way?
Wednesday.
Wednesday, okay. So this would be, trouble Thursday today, but that's okay. Okay, so this is 3 p.m. on a Wednesday. This is 4 p.m. on a Wednesday. Same Wednesday. 5 p.m. on Wednesday, 6 p.m. on Wednesday, 7 p.m. on Wednesday, 8 p.m. on Wednesday, 9 p.m. on Wednesday, 10 p.m. on Wednesday, 11 p.m. on Wednesday, and 12 p.m. on Wednesday. Okay, you got it? 12 p.m. on Wednesday.
AM.
Wait, no, I said.
I'm sorry.
Yeah.
AM.
That's okay. Wednesday, Thursday, AM.
Okay. Let's go back and do it again. 3 p.m. on Wednesday. No, I was doing it backwards. 3 p.m. Wednesday. 2 p.m. Wednesday. 1 p.m. Wednesday. 12 noon on Wednesday. 11 a.m. on Wednesday. 10 a.m. on Wednesday. 9 a.m. on Wednesday. 8 a.m. on Wednesday. 7 a.m. on Wednesday. 6 a.m. on Wednesday. 5 a.m. on Wednesday. 4 a.m. on Wednesday. 3 a.m. on Wednesday. Okay, right there. 3 a.m. on Wednesday. Okay? Going this way, 4 p.m. on Wednesday. 5 p.m. on Wednesday. Did I change my days there? Okay. 5 p.m. on Wednesday, 6 p.m. on Wednesday, 7 p.m. on Wednesday, 8 p.m. on Wednesday, 9 p.m. on Wednesday, 10 p.m. on Wednesday, 11 p.m. on Wednesday, 12 midnight. So now it's Thursday. 1 a.m. on Thursday, 2 a.m. on Thursday, 3 a.m. on Thursday. Coming this way it was Wednesday, this day it's Thursday. Okay, so we call this line right here 180 degree parallel. We call it the international date line. When you cross that, you go up a day or back a day. Okay? You have to. Okay? You got to. Okay? Now, and that's called the international date line. 180. And remember I said there was a special name for it? I wasn't going to tell you yet. Call it here. The international date line is the 180 degree meridian, exactly on the opposite side of the globe of the prime meridian. Now, here's a dumb Navy story. I don't know that this was true, but I heard it said while I was in the Navy, that somewhere in the Pacific, there was an island that crossed that the 180 meridian, the international date line, went right through that island. Now, I don't know, it may have been Vanalua. That looks like it crosses it, but it could be any one of these few little islands here that goes right through the international date line. Now, you sort of have to have an understanding of what the naval mindset is. Okay? It was an island there, right through the internet. Supposedly, somebody bought some land that crossed on that island right across the international date line. They bought that land and built them a bar on that land. And part of the bar was on one side of the international date line and one was on the other side. So therefore, when it turned Sunday on this one, it was Saturday on this one. When it turned Sunday on this one, it was Monday on that one. So they could just go from one end of the bar to the other. If they had to close on Sunday, they just opened on the other side of the bar. Now, whether that actually happened, I don't know. But supposedly, that was the urban myth, or the...
What city?
We got a club in called the Alabama Mississippi line.
Right.
It's literally on the line like that. I mean, I don't know if that's why they did it or whatever, but that part of Alabama doesn't serve, like you say, alcohol on Sundays and stuff, but Mississippi side does. You know?
Oh, I see. Okay. Yeah.
So it's probably legit.
It may, I mean, if it was Old Sailor that did it, I believe it. I mean, they focus their life. Yeah, never mind. Okay. That's what they live for, it seemed like. Okay.
I thought they live to cuss.
Huh? And they cuss like a sailor too, that right. You didn't have to bring that up. No. All right. All right. So there's your international date line. One side of it, you're on one day, the other side. Now, when I was on the ship in the Navy crossing the Pacific, of course, every few days we crossed another time zone. And it was so bizarre, well, they did it on purpose this way. When you had to add an hour because you crossed the time zone, it was always adding. In the Navy, we stand watches, 4-hour watches. There's the mid-watch from 4 a.m., midnight to 4 a.m., then the morning watch from 4 a.m. to 8 a.m. Now, the people coming on to watch ate breakfast early, and the people going off watch ate breakfast late, so you can do that all right. And then 8 to 12, that's the morning watch, basically, not early morning watch. And then the people who were coming on the 12 to 4, they ate lunch early, and the people coming off ate lunch a little later. And that was easy to do. And then the 4 to 8, well, that would have spanned right across supper time. And if we cuss, we eat too, But anyway, so they did what they call a dog watch in the evening. 4 to 6 and 6 to 8. So therefore, the people, you only had a 2-hour watch at that one. Okay? And then 6 to 8, and then 8 to 12 again. Okay. Well, when we were crossing and adding an hour, crossing the time zone that way, they always added the hour during the dog watch. So nobody had a 5-hour watch. They had a 3-hour watch instead. But when they were crossing the other way and you were losing the hour, it was always the mid-watch. And those people who were standing watch then were very happy to only have to be up for 4 hours in the middle of the night. They were only up for 3, but everybody else lost an hour's sleep that night, okay? Always that way. But those times that we crossed the international date line, and I know they rigged this, it wasn't we really crossed it then. If it was an extra day, it was always an extra day, sometime Monday through Friday, whatever day we really crossed. If we lost a day, it was always a Saturday. Always a Saturday we lost. We never lost a working day. We always lost a weekend, and we never added a weekend day. No matter when we crossed it, they added a day during the week. They always got us coming and going, But basically, you're out to sea, there's not much difference anyway. But a little bit. Okay, enough of that. And sea stories to boot.
What time is it?
It's almost time. Let's see what the next slide is. This also shows the international date line takes a little bit of a curve in it. Because it's coming down here, and this end of Siberia would be on a different day from the rest of Siberia. This is part of Russia. So they jig it over here, but then they have to go back this way because the Aleutian Islands, which are part of Alaska, some of them would be on another day, so they swing it back here to miss that. Then it goes pretty straight here, but then there's a group of islands called Micronesia or something like that, and then also New Zealand has several islands around it and they want to keep them on the same day, so they jig it over here for a while and then come back when you're outside of that. So there are some variations, local variations in the international date line, so they can do that. I was guessing it was that island right there that had the bar, but I don't know that for sure. Okay. All right. Any, let's see. We will pick up next time with yearly time. There are a couple of examples given in the book, and it's a pretty interesting thing. How many time zones is Honolulu, Hawaii, and they give the latitude and longitude behind New York City, latitude and longitude, which that has something to do with the time zones and which does not. Latitude has nothing to do with time zone. It's the longitude. Take the difference of those, divide by 15, and you've got approximately how many time zone differences. Okay? So I'll let you play with that if you're interested. All right, we're ready for the lab. Do you want to take a quick break before we do? I know y'all been sitting a long time. I get to walk around some, but y'all don't. So let's do a quick. I hope all of you have a copy of the lab. I've put them out in most places. And the strange thing about this is, even though it's sort of designed to be the Chapter 15 lab, it really is doing a lot of stuff we just did in 16 as well. In fact, everything we did about the noons and days and stuff like this, that's stuff we did in Chapter 16. So these labs don't fit exactly, but we need a lab for each chapter, so this is what it's called. Later, we'll do another lab that does latitude and longitude, but that's where we're going to be on the geology and earth science, okay? So they all don't fit exactly, but they all have to do with what we're studying. So some of them will be lagging, some of them may be leading. Well, I try not to lead with them, but lag is fine. All right, so what we're talking about noon. What is noon? Technically, what's noon? When the sun crosses or transits your local meridian. Highest point of the sky. It's not always at that day or time, that time. We do it based on a clock, which is not based on the sun. It's an average of what's on the sun. Okay? The interval from one noon to the next noon is what we call a solar day. If we're basing it on the sun crosses maximum height, crossing transit our meridian on one day to the next day. That's going to be on average 24 hours, but it won't always be exactly 24 hours. Okay. Now, what do we call the times in the morning? We just talked about AM. What does that stand for? Ante-meridian, which means before meridian, before it crosses the meridian. And PM is post-meridian, after that, after it crosses the meridian. So that's where we get AM and PM. Okay? By the way, those are Latin words are based in that. Okay? Before the meridian and after the meridian. Whereas post-meridian is after meridian, AM is not after the meridian, it's before the meridian. Pre-meridian. So it's sort of backwards even for our spelling. Okay. There were some weird things that happened in the past. They talk about these, what the Romans did. It was totally bizarre. But anyway, we'll let them get away with it. So you can read that first page and a half and deal with that. Okay? Now, solar versus sidereal day. Again, things we talked about in this chapter's lectures, but it really is the lab we're going to be doing here. So actually it worked out pretty well. We are doing it on the same day. The solar day is based on the sun crossing our local meridian, whereas the sidereal day would be if at night we had the star transiting the same star. We are able to pick out that bright star when it crosses our meridian from one crossing to the next. That would be our sidereal day. Now, I'm going to go on and shut down this. Yeah, everybody who's come in got a lab, right? I wasn't sure where everybody was sitting. I tried to hit all the desks where you were. Boy, there's the very thing right here. All right. Sorry, I should have thought to do this sooner, but okay. Okay. Now, the sun moves 360 degrees around the ecliptic in 365 days. That's almost a degree a day. A little bit less, but almost that. So the sun moves about 1 degree per day along the ecliptic. Not very much, okay? Now, therefore the sun is about 1 degree east of the vernal equinox the day after the vernal equinox. Calculate how long you would have to wait until, and this is making a reference to the picture you see, figure 48.1b. That's this figure here. Here is the sun, local celestial meridian, crossing our local celestial meridian on the vernal equinox. The next day, here is our local celestial meridian. The sun is here. It hasn't quite reached the local meridian. How much longer does it have to go? Okay? That was the question. All right? That's what I was referring to. So, calculate how long you would have to wait after the situation depicted on figure 48.1b so that the sun is crossing our meridian that day. So if we know that it crosses, let me get my pen back again, okay, 1 degree, okay, that is to okay, 1 degree is how many minutes? 60 minutes. So let's change that 1 degree to 60 minutes. Okay? Okay. I don't think we really need to, but yeah, we will. Okay? Okay. Let's get our ratio first. I always start to do this one way, but realize I'm skipping a bunch of steps. Okay. In 300, okay. Yeah, I got you. Okay, make sure. Remind me at 3:45. I got to stop and call roll. Okay, let me do that while I'm thinking about it. 360 degrees is how far the Earth spins in 1 day. How long is that? 24 hours. Okay. That gets degree per time, right? Okay. So what is that ratio? 15 degrees per hour. Okay. But that hour is 60 minutes, right? So how many minutes would it take to do 1 degree? Minutes would it take to do 1 degree? Okay, I'm sorry, I put this in the wrong place. Wait a minute. Let me get my ratio right. Okay, I'm going to change that ratio from degree per hour to 15 degrees is to 60 minutes. Okay, as 1 degree is to how many minutes? That is 4 minutes. You're absolutely right. So that's the answer to that. Express our your answer in minutes. That's why I had to make the change there. 4 minutes. Okay? 4 minutes. So that's why, I wish I left the slides up now. Remember on the slide, 1 sidereal day is about 4 minutes. A solar day is 4 minutes longer than a sidereal day. That's why. Right there. Okay. So we've described one way of showing that a solar day is a little bit longer, 4 minutes longer than a sidereal day. Okay. And then it talks about some more stuff, figure 48.2. That's another illustration of that, same type thing. Now, notice question 2 here. Only trouble is, I can't find the question. It says that figure 48.3 depicts the sun's Earth. Here's the sun, there's the Earth, and on the opposite side of the sun are your constellations of the zodiac. There's Leo, Cancer, Gemini, Taurus, Aries, Pisces, Aquarius, Capricornus, or whatever you call that, Sagittarius, Scorpion, Libra, Virgo, and back to Leo again. Those are the constellations. How you get those things out of that, I don't know. I mean, I do not know, but Leo, the lines, kind of I can sort of see. Taurus, the bull, I'm not sure I ever see. Aries, what in the world is that? It's just a bunch of stars up there. I don't know what it is. Scorpio looks sort of like a scorpion. It really does. That one comes pretty close. But a lot of the others, where in the world do they get that? Okay? I think Sagittarius may be some type of warrior or something. Maybe someone shooting an arrow. I think that's what it is.
It's supposed to be a centaur.
What's that?
It's supposed to be a centaur.
Centaur? Oh, okay, that's what it is. Okay.
You can see Gemini, the twins.
Okay. If they look more alike, I would think they were twins. But yeah, it seemed like they're conjoined twins. They share an arm or something. I don't know. But anyway, we won't go into that either. Pisces, I guess, is supposed to look like a fish. You know, I don't know. And some of them overlap, so I don't know how they do that. But anyway, that's what it's referring to. The sun's apparent motion along the ecliptic, where the zodiacal constellations are found, is in a heliocentric perspective. As the Earth orbits around the line of sight of the sun toward the background, stars also move. For example, in the diagram shows the sun in Leo. A month later, the Earth will have moved enough so that Virgo lies behind the sun. Okay? Where is the question there? There's not one. I don't know why they said all that. They never asked you to do anything, so there's nothing to do. So number 2 has no answer because I can't find the question there. Okay.
So that's what I'm talking about.
What's that?
That's what I'm talking about.
All right. She likes that one. All right. Then, part A is talking about the analemma. Didn't we discuss that today in class? So this is actually fitting better than it should. It's just this is the lab for the last chapter, not this chapter. But it's fine. Okay? And you can read that. It describes what the analemma is. And by the way, as in the book, we said analemma is another name for the equation of time. But this also says the analemma is another name for a sundial. We think of a sundial as a thing that casts a shadow on the clock face, but the analemma is a different type of sundial, which is that figure 8 on the floor, or wherever. So it's a closed serve resembling a flat bottom figure 8. Figure 8-4. There it is, folks. There's your analemma. Notice it's fatter on the bottom, skinnier at the top. That relates to the speed at which we're going. Okay? Around about December to January time frame, we're at January, we're at the closest point we are to the sun, so therefore we're moving faster. And up around July, we're at the farthest point from the sun, so we're moving slower, so the it takes longer for us to go from what, I mean, anyway. So that's what makes it fatter. Notice this is a kind of a three-dimensional plot. The vertical dimension here is the declination of the sun, which is how high the sun is north or south of the celestial equator. They just say equator here, but it's the celestial equator. And when is it on the celestial equator? Approximately what dates? March 21st, September 21st or 2nd. And sure enough, that's right when it's crossing there. So you see this is declination. When is it farthest from the celestial equator? Say again? December and June, around the 21st or so. And sure enough, that's when you're at the maximum end. And there you're at what declination? On the solstices. What's your declination of the sun then? 23 and a half. 23 and a half. Okay. So, you've got that. So, declination of the sun is on the vertical axis. But you got on the horizontal axis, they actually have two of them. And this one is time in minutes. The one down here is degrees. We're not really worried about the degrees. So, we're going to worry with the time in minutes. Okay? And then the third thing that's shown on here is the time of the year. And that's on the scale on the analemma here. You see each month, January, February, March, April, May, June, and so on. Okay? January, February, March, April, May, June, July, August, September, October, November, December. So there are your months. So it's really a three-dimensional graph in two dimensions. So it's a pretty handy little thing to have. And that's what we're going to use for just about all the rest of the lab. Okay? You can read the next part, and I've already talked about some of that. The fact that we're at an angle, that gives us the vertical scale there, the 23.5 degrees north and south. And the fact that we're traveling at different speeds because we're in an elliptical orbit, that gives you the thickness and thinness of that figure 8.
Mr. Fowler.
Yes.
I'm missing some sheets.
I'm sorry?
I'm missing some sheets.
I can't hear.
They not all here.
What's not?
You on?
Oh my goodness.
Yeah.
How many are missing pages? Just you?
I think she's missing the last 2 pages.
What's that?
I think she's missing the last 2 pages. Right? That's
Okay. Does everybody have this as the last page? Okay.
That one?
I have it on there.
Right. Yeah, she needs the last 2 pages.
Okay, here's the swap. You've already written it up.
Yeah, read
Okay,
on.
let me. I put them there to be copied and.
Thank you.
Okay.
So I just gotten another tornado warning this time. I guess if we're going to be dismissed, it would be on Food Alert or something.
Yeah,
Okay.
probably.
I just.
They was just downtown about 30, 45 minutes ago.
Birmingham.
Downtown what?
Birmingham.
Warning.
Really?
Yeah. Not a watch, a warning.
Okay.
They said put me in touch downtown. It was,
Have y'all heard of?
I haven't.
I am so surprised. Huh? What did it say? That we're under a
Watch.
That's all I got.
yeah, a watch, but not a warning.
It's like right now it's in Fayetteville.
Fayetteville.
Tennessee?
That's pretty far.
Yeah.
It's on there.
I didn't know there was a bad
Yeah.
And then Pittsburgh.
There's one in Georgia too.
I'm from North Alabama, so I hear about Fayetteville, Tennessee all the time.
Okay. So you're the only one who was missing 2 pages. I don't know how that happened. I'm hoping that can't think of the guy who left early.
Hunter.
Huh? Who?
Hunter? Hunter is his name?
Hunter.
That dude?
Yeah. Maybe he has 2 extra pages. I don't know. All right. So anyway, you can read the next few pages. I've just discussed some of it. By the way, we mentioned him in class, but here he is again, Johannes Kepler. He could be a paper topic. Is Kepler's laws of planetary motion, that could be a paper topic. Lots of things here that you could choose from. So here we got that. All right. Now, number 3. Remember, number 2 didn't have one. Here's number 3. Briefly describe the effect on the shape of the analemma if the ecliptic equator angle were to increase, like going from 23.5 to 24 or 25. What would happen to the shape of the analemma then? If you were to increase the angle, what do you think would happen? Say again? Where do you find, what does that affect on the analemma?
Is that the through the middle?
Okay. What is the angle that we have? 23.5 degrees. Do you see that anywhere on here? On the analemma? That's from the 23.5 is the bottom of the figure 8. 23.5 north is the top of the figure 8. So what would happen if you increase that? It would stretch it vertically. Stretch it vertically, right? All right, so that's number 3. Briefly describe the effect on the shape of the analemma if the ecliptic equator angle were to increase. The analemma would be stretched vertically. Probably not affected any horizontally, you might say. It wouldn't get fatter or thinner necessarily. It would stretch vertically.
3:45.
It is 3:45. Thank you. Let me call roll quickly. Well, I don't do anything quickly, but let me call roll. Hunter had to be gone. LaShandra's still here. Rachel's still here. Trey is still here. I saw you. Yeah, there you are. Okay. Ray is still here. Jarrell, did we lose Jarrell? It does look like we did. Cece is still here. All right. Anthony didn't make it in today that I've seen yet. I think we lost Sean too, didn't we? Okay. Fred never made it in today. Chelsea is still here. She moved around on me some, but she's still here. Oh, that was the other class you. Yeah, that's you constantly have me confused. Okay. Sam didn't make it in today. Nick is still here. Melva's still here, right? Or did she just leave? Or?
I think she just went to the bathroom.
Okay, her stuff's still here, so I'll get her when she comes in. Willie's still here. Lisa's still here. Tiara, yep, is still here. Angela is still here, yep. Ashlyn just decided to leave. And Kedrick is still here. Okay, I'm going to count the people who are in the room now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2. Yeah, Melva's doing this to me. She knew I was calling roll again. Yeah, there you are. Okay. Count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 2, 4, 6, 8, 10, 12, 13. Okay. I'll catch the others when they come back. All right. Obtain from your instructor the latitude of your location and fill it in below. Does anyone remember what it was? 33 degrees, 23 minutes, and 45 seconds. Got it. That's for Alabama. Pretty close anyway. Okay? Now, right under that it says, determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Okay? Now, what I'm going to have to do, I think, is erase all that I've got on here. Everybody got it?
No.
Oh,
33,
23,
7-4.
that was the number 4 latitude. Okay. Oh yeah. That's still here. Okay. Now, all right, let's draw our globe here. Here we are standing in Bessemer, Alabama. Okay. There's our zenith is directly overhead. Okay. We're at 33 degrees, 23 minutes, 45 seconds over the celestial, that's our latitude on the globe. On the celestial sphere, that would define where our celestial equator is. 33 degrees, 23 minutes, and 45 seconds. Okay? That's that angle there. It says determine the altitude over the southern horizon of the intersection of this celestial equator and our local celestial meridian. That is our local celestial meridian, so we're asking what is that angle there. You subtract it from this from 90. Except rather than doing 90, what will we do? 89 degrees, 59 minutes, and 60 seconds. That makes it easier to do the subtraction. Okay? Okay, subtract the 33, 23, 45 from that, and it makes the subtraction so easy. What is it? Say again? Why did I write it that way? Is that the question? It's 90 degrees, right?
Yeah.
Well, 60 seconds is how many minutes? 1. So you add 1 to 59 and you get 60 minutes. And 60 minutes is how many degrees? 1. Okay, so that makes 90. It just makes the subtraction easier to do it this way. Otherwise, you have to borrow. Okay? So write it this way and it makes it easier to do. You've already borrowed. So what does that come out being? Can you do the subtraction? 56 degrees. Say again? 36, 15. All right, good deal. That's the angle of the celestial equator above the southern horizon. Celestial equator, southern horizon, northern horizon. That's it. All right. So that would be in between 4 and 5. Okay? Now.
Okay, I thought it was
What's that?
15 degrees.
What?
In and out. Sorry.
Okay, wait.
I think what she's saying, okay, you got the 90, right? If
Okay.
you want to break it down, you do the 89, 59, and 60 because the 59 and 60 creates 1 hour,
Right.
Which,
1 minute. This makes 1 minute. Add that to this, you get 60 minutes. 60 minutes. 1 minute makes. Okay. Now don't be confusing time minutes with degree minutes.
okay, because I thought 15 and an hour was.
Okay. Yeah. Okay. What you're thinking of is what's the relationship between 360 degrees around the globe and hours of time, which is 24 hours to go for this it to spin one time. That's that. When we're talking these degrees of minutes, minutes and seconds, these are not time minutes and seconds. These are fractions of a degree. And that's 60 and 60, just like it is for time, but these are arcs. These are arc, not time. Okay? Not based on hours. Okay. Nothing here is dealing with time yet. This is all just angles. Okay.
What question?
Yeah.
What answer is that?
I'm sorry?
What answer?
24 and 5.
Okay. Okay. Number 4 on the line there is this right here. Latitude of our location, that's it right here. It's down here too, but you can't read it. This is a little easier to read up here. Then in between, when it says determine at number 5, that's what's there. You just subtract this from 90 degrees, which I made at 89, 59, 60. Okay? Now, use the figure 48.4, which you turn back one page. 48.4, that's your analemma. And your answer in step 4, which is what we just did, to fill in the table 48.1, which is just below. Now, someone, when they made the lab manual, they forgot they wanted to put in an extra lab, and they named it 47.1, but I corrected that to 48.1, okay? So what you do is find the declination of the sun on February 15th. So where are you going, what do you look for first? February 15th. Has everybody found it?
Yeah.
Okay. Declination of the sun would
13
be?
degrees.
Is what?
Minus 13 degrees.
Minus 13 degrees or 13 degrees south. Whichever you want to do it. The way they listed here is 13 degrees south. I can understand minus 13 too. Okay? All right? Now, it says here the next thing is noon altitude of the sun at your location if the declination of the sun was 13 degrees south. Well, here is what is declination measured from?
23.
Okay. Look here. Where is that 13 degrees measured from? South of the equator. Okay? This is the celestial equator. So we do, what do we say, 13 degrees? 13 degrees south of that. So guess what we do? Here is the sun on the 15th of February. My throat's going. My voice is going. It's 15 degrees south of the celestial equator. So is it 13 degrees? No, 13 degrees, you're right. 13 degrees south of the celestial equator. So what is the altitude of it? Celestial equator was at 56, 36, 15. Subtract 13 from that. And what do we get? 43 degrees, 36 minutes, 15 seconds. You see that? South of celestial, the declination of the sun is south of that. Okay? There we have it. Now the question is the noon altitude. Whoa. Okay. Let's go on and do all of them for our location. June 21st. What's the declination of the sun on June 21st? You should be able to give it to me without looking. Say again? 23.5 degrees. We know that one, right? Okay, 23.5 degrees. Which way? North. So that's north of what? The celestial equator. So this time we'll do the 56 degrees, 36 minutes, 15 seconds. This time we'll add 23 degrees, 30 minutes. That's 23.5 degrees, by the way. When you add those, what do you get? 89 degrees. Wait, that's 79, isn't it? Someone's trying to confuse me. Okay. 79 degrees, 66 minutes, 15 seconds. What's 66 minutes?
Another hour.
Not hour.
So it's 80 degrees.
Degree, another degree.
Yeah, another degree.
it's 80 degrees. 80 degrees, 6 minutes, 15 seconds. Right? Because when you pass 60, that adds another degree here. 80 degrees, 6 minutes, and 15 seconds. Okay? All right. How about October 15th? What's declination of the sun?
8 degrees south.
Say again?
8 degrees south.
8 degrees south.
8 degrees south. That looks pretty good to me. So that'd be 8 degrees south of the celestial equator, which would be, the celestial equator is at 56 degrees, 36 minutes, 15 seconds. And we're going to subtract 8 degrees from that. And what does that leave us? 48 degrees, 36 minutes, 15 seconds. All right, good deal. What's that?
That's for October?
That's, yeah, October, what was it, 15th? Yeah, October 15th. All right. And the last one is,
Oh, we gotta find a new altitude.
what's that?
Go ahead. December 26th.
Okay. We're doing the noon altitudes at our location. We're doing all these right now. Okay. And then December 22nd, declination was what?
23.5 degrees.
Yeah, 23.5 degrees south. Okay. So we take our 56 degrees, 36 minutes, 15 seconds, and subtract 23 degrees, 30 minutes. And what does that give us? 33 degrees. Say again? 6 minutes, 15 seconds. So that's the noon altitude of the sun on December 22nd. Okay? What's that?
28 degrees, 36.
Okay. We did all those for our location. Okay? Now we got to turn the globe a little bit and do Altegard, Norway. So, is it all right to start erasing? You still need a little longer? Would it help to turn off the light over here? Does it make it easier to read? I forgot we'd be doing this much writing. Does that make it any easier?
Yes, thank you.
Okay. Ashley's wanting to go back to sleep, so she went away. Okay. I'm sorry I write all over the board, but I have just such a small screen to write on. And it lays down on me. It's trying to go to sleep too. Okay. Y'all ready to move north to Altegard, Norway? Has everybody got that one done? Or are you still working on it? Move ahead? Help me? No. Okay. I keep getting a signal to move, so let's do it. So I'm going to erase parts of this. I'm not going to do the whole thing because it's too painful to do it all. And this will take a little bit of time, but I didn't want to do it while you were still writing. Zenith stays the same, but celestial equator will be moving. Probably going to have to put a coat on this guy, but we'll see. Get out of there. All right. We're almost there. It takes a long time to get to Altgard, Norway, by the way. Okay. All right. Altgard, Norway, the latitude is 7 degrees north. So that's going to be something like that. 70 degrees north. So that means our celestial equator is over here, right? That this is 70 degrees north. Okay? I don't have to put the north in there. Let me just put 70 degrees. Because that may get in our way later. Okay? Now, what is going to be the altitude of the celestial equator? 20, exactly. 20 degrees. Okay, we got that now. Now, we already have declination of the sun on February 15th. You wrote that down, didn't you?
Yeah.
What was it?
Minus 13 degrees, 13 south.
Okay, so what would be the noon altitude of the sun at that time, February 15th? That's 13 degrees below the celestial equator. So what would that be left at? 7. That's the highest it gets on February 15th, at 7 degrees above the horizon. Whoa. This is the sun on 15th February. At noon. At noon. What's that? This was 20. This is 13 degrees south of the celestial equator, so that leaves 7. My line isn't good. It should be down here somewhere. Okay. If you're trying. What's that? If the latitude is 70, that leaves 60 below that. And if that's celestial equator, because that's 70 here, then if the sun is 13 degrees below the celestial equator, that leaves you 7. 7 degrees is as high as the sun gets on February 15th. And I guarantee you it's not been up there for long either. It probably rose about 10:30 that morning and set about 1:30 that afternoon or something like that. Very short day. Only got up to 7 degrees. Okay? How about June 21st? Where was the declination of the sun on that day? 23 and a half. So this, yeah, June 21st, and that was north or south? North. So that's another 23 degrees further here, 23 degrees, 30 minutes here. So this is the sun on the 21st of June. Okay? So what would be its altitude? This was 20, 23 and a half degrees. North of that would be 43 and a half degrees. It doesn't even get halfway up that day. Not even halfway up on the longest day of the year. And guess what? It never sets that day either. That means at midnight it was probably just over the horizon, and then it slowly went up to about 43 and a half degrees, and then started setting from then and never set. It went right back on the horizon and just kept doing that. You had 24 hours of daylight, but the sun was never very high in the sky. Ever. Okay? See that? All right. What was the declination of the sun on October the 15th? South. So that would be somewhere about like this, 8 degrees south. So what would its altitude have been? 12 degrees. So you're right. So here's the sun on the, whatever day it was, 11th was it? 15th. 15th of October. Okay? So it was 12 degrees. So it got a little higher than it did on February 15th, but not much.
So like south you trade.
South you go below the celestial equator, north can go above the celestial equator. Okay? See, north is that way, south is that way. How about December the 22nd? 23.5 degrees south. So the sun would be somewhere like there. Guess what? Say again? What's that? No daylight. It never came up. The highest close it ever got to coming up was 3.5 degrees below the horizon. So you may have gotten a little bit of twilight-like lightning on noon. You know, it got a little brighter, like you might see the sun, but you never saw it. Sort of like the early morning when it starts getting a little brighter, but the sun hasn't come up yet. That's what. Yes.
So it's 0 on December 22, no degrees?
Oh, you don't put anything. It never rises. Never rises. You never see the sun on December 22nd. Because guess what? 70 degrees is north of what circle? The Arctic Circle. Okay? North of the Arctic Circle. So sun never going to come up on December 22nd. Okay? All right. Almost time for a nap, isn't it, Rip? No. Okay? This is historic, folkloric. Okay? Whoa, I almost.
You seem tired today. You usually don't.
What's that?
You seem tired today.
I seem like it? Is she trying to get me to end class early or something? Actually, let me tell you, by Thursday afternoon, I am tired. Okay, because at this point in the day, I started teaching this morning at 8 o'clock. I got here at 7:45 or before, and I taught up until 12:15. Then I had really less than an hour before 1:15. So I've been going at it almost solid, except that. A little bit less than an hour over lunch. So I am tired. And by Thursday, really tired. Okay.
How long have you been teaching science?
I've been teaching at this building. We weren't Lawson then. We were Veteran State Tech. I just passed my 20 years, so I'm on my 21st year now.
Surely you taught like 8th grade science or something.
I taught 8th grade biology. I was a substitute teacher and taught for from late September to December, but not for very long. I was just a substitute. I went back to grad school in January, so I couldn't do. But no, that was the only time I did some substitute teaching, but most of the time I've taught in the college level. Okay, well, I'm acting more like a middle school teacher, huh?
Oh, very much so. From 1982, yes.
From what?
Remind me of
1982,
yes. I am going, this is a time warp. Every time I come in here, just like my 8th grade science.
Really?
Exact, that many days. Exactly.
I don't think I'm offended by that at all. Okay, so yeah.
It's not offensive. It's just very,
All right. Rip Van Winkle, that's what I was talking about, taking a nap. Okay, awakens from his extended slumber and asks a passerby what year it is so that he can determine how long he slept. The passerby quickly responds, I wonder why he's so quick. His beard's about this long and the smell is never okay. Anyway, rapidly moves away. Realizing that a 20-year snooze might be a world record, he thinks he should pin down the date as well as the year. So he moves out from under that big old tree where he was sleeping for 20 years and measures the altitude of the sun when it crossed his meridian. Boy, this guy knew his stuff, okay? He measured the altitude of the sun when it reached its peak, crossed its meridian, and he finds that to be 44 degrees over the southern horizon. So that's going to be, let me get my pen back, something like that. 44 degrees above the southern horizon. That's where the sun is when Rip woke up. Okay? He knows that the latitude of his chosen spot on the Hudson River in New York is 42 degrees. So his latitude here is 42 degrees, which would make this to be 42 degrees, right? That's his latitude. So this would be, what line does this represent right here? Celestial equator. You got it, because his latitude is above the Earth's equator, so this line is zenith is above the celestial equator. Okay? 42 degrees. Now, from that, what can we determine? Oh, if that's 42 degrees, how many degrees is this? How many? 48. Very good. 48 degrees. So, what does that tell us? What does this angle represent? The what? Declination of the sun at noon that day. And how far would that be? 4 degrees. You're right. 4 degrees. North or south?
North. South.
Okay, multiple choice here. Okay. It's below the celestial equator, right?
It's below the what? Oh, yes. Okay.
So, now, so we go back, and he happened to have an analemma real close by, wouldn't he? Okay. 4 degrees south of the celestial equator. And what two possible dates was that he woke up? Okay, going the other way, I think it's October 4th, maybe? Okay. And going across 4 degrees until you get to March the, looks like probably the 11th. Okay, October 4th or March the 11th. So it said, the question was, on what two possible dates could he have awakened? And you just told me? Or October 4th. Is that what you said? Now, he also looks at the tree a little bit and notice that it's just beginning to bud. So which date would that have been?
March the 11th.
That would have been the March date, because it would have had leaves falling in October, so it would have been budding on March. So that asked for 3 different answers, 2 possible dates, and which one was the date of his awakening. You should have 3 dates there. 2 of them are the same. Okay. What's that? Okay, how much?
You said March 4th, right?
That's what somebody said, yeah.
It's October 4th.
No, it was October 4th and March the 11th. And he woke up on March the 11th. Why? Because the trees were budding, not falling. Okay, the leaves were budding, not falling. All right. Everybody got it? As we saw previously, the analemma graphs daily differences between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma and figure, and here they left it out the digit altogether, is 48.4 that we were just looking at, to see that on October 15th, find October 15th, there it is, and that the sun will cross the meridian 14 minutes, so you go up to the vertical horizontal axis, but it's the one on the top. What do we say, October 15th? Yeah. Go up that line and you see your 14 minutes, right? Before clock noon. So anything on the left side is before clock noon, on the right side is after clock noon. Okay? You see that? No? Okay, yes, okay. So anything over here is that many minutes before clock noon. Over on the right-hand side is that many minutes after clock noon. Okay, that was just your reference point. Okay. So, number 7. For the dates given in the table below, use the analemma in figure 48.3, they got it right this time, to determine whether the actual sun will cross the meridian before or after clock noon. So the first column here, after the date, you write one of two words, before or after. Actually, you may find you might have to make another choice somewhere there. And then, in the right-hand column, you put the amount of time, that would be number of minutes, before or after clock noon. So the middle column is going to be before or after, the right-hand column is going to be so many minutes. So January 10th. January 10th sure does look like after to me.
I said before.
And how many minutes?
7.
Boy, they make you go a long way. Yeah, looks like it. 7 minutes. After clock noon. February 15th. Before or after?
After
After. How many minutes?
13,
Is it 13?
17,
This is 17. Hike. No.
64.
Okay. February 15th. Go up that line, up that line, up that line. It looks like 14 minutes to me.
Oh
Wrong
my goodness.
Oh my goodness.
7.
All right. April 15th, Text Day. That's important, isn't it?
No.
April 15th.
That's 2.
Is what?
After.
It's just barely after.
Barely after.
Wouldn't you say less than a minute?
Yes, a minute.
Okay, after, but less than a minute. So on tax day, it's almost right at clock noon, so you don't have to worry about that. Okay?
So it's
As if you would.
After less than a minute.
After and less than a minute. I'm on the wrong page. Oh, here we are. Wait, if you don't. July 30th.
January after 7.
Are we after again? Here we are. How many minutes after?
3 minutes. 5 3/4.
July 30th. If I go up there, that looks like it. Okay, it's definitely after, right?
Yep.
But it looks like it's about 6.5, doesn't it?
Yeah.
just past 6.
No, it's July 30th, isn't it?
Yeah.
July 30th.
Yeah, 6.5.
Yeah,
Oh, isn't it 6.5? Got it?
Yeah.
Make sure you understand.
So what if it's before and after?
What's that?
What if it's neither? Then what you mean?
Okay, you can put neither, or right on, or something like that. Okay, it's September 1st, is that one you're talking about?
Yeah.
September 1st. I can't find it. Where is it? There it is. September the 1st. Yeah, I can't tell. It looks like, yeah.
Your little graph should be on
Early.
opposite this tree.
I don't think it's even a minute. Do you?
Less than a minute.
I would say less than a minute. Did you say before or after? After. Just barely after, less than a minute. How about October 30th? Before or after? Before. And how many minutes?
Like 9.
October the 30th?
No, right.
Okay. Find October and find the days going from 5, 10, 15, 20, 25, 30. Huh?
About 15
I I'd say it's right around 16 minutes.
17:30.
Before, right?
Is it October 10th?
What's that again?
October 10th.
I thought it was October 30th.
Oh, geez, why did you do that?
Okay.
October 30th.
I think the numbers are changing on these pages here.
They are,
30th on 10.
they're telling me.
It's what?
October 30th, October 30th on 10.
Yes.
Okay, are you
Oh,
sure
wait,
you're not
no,
looking at
no,
September
no,
30th?
Now you gotta go up top.
See October, you see the 5, 10, 15, 20, 25, 30, that's the 30 that goes with October.
Also, it goes like.
Yeah, the days get greater. Yes, okay. All right. How y'all doing, okay? Okay. Then we turn to the last page yet. All right. We're back to our local meridian. Okay, so let me change a few things here. Back home again. And you remind me where we are, our local meridian. Bessemer, Alabama, good deal. Okay, that would be 33 degrees, 23 minutes, 45 seconds. So that would be somewhere about that, maybe too much, I don't know. So that's 33 degrees, 23 minutes, 45 seconds. So what's our, that's what does that define right there? Say again? Celestial equator, you got it. Okay? Now, that would make this angle here. Do you remember what that one was? Okay, subtract it from 89, 59, 60. I thought y'all would remember that.
56, 36, 56.
Say again? 56 degrees. What'd you say? 36 minutes and 15 seconds. Okay? That's the altitude of the celestial equator above our celestial horizon. Okay? Now it said determine the altitude over the celestial horizon of the actual sun on May 15th. What can we learn about May 15th? May 15th, you're 19 degrees what? North of the celestial equator. So you, another 19 here. Add that to the, I didn't draw it big enough, but you got it. Add it to the 56, and that would be 75 degrees, 36 minutes, 15 seconds, right? On May 15th. All right.
The altitude, no.
Say again? That's your altitude of the sun.
The 75, 36, 15?
Yeah, 75, 15, 75, 36, 15. All right. Everybody see that? Okay, really? Okay. All right. You want to go on and figure out the time then, since you got May 15th pegged there? May 15th would be 4 minutes. Which side? No. Before noon. And what's 4 minutes before noon? 11:56. That's the time when the sun crosses the meridian. 11:56. All right. That's June 15th.
AM or PM?
Right, okay.
Yeah. Oh yeah. Before noon, so it would be AM. That's right. 11:56 p.m. would be just before midnight. Yeah. After meridian. Okay? So, June 15th would be, it looks like about 23 degrees north. 23 degrees north, so you add that to 56. 79 degrees, 36 minutes, 15 seconds. Okay? That would be the altitude of the sun. What time does it cross the meridian? 12 o'clock on the nose, or as close as I can get it to being on the nose. Okay? November 4th. What you get?
15 degrees south.
15 degrees south of the celestial equator. So you subtract that from 56. Yeah. Really?
Yeah.
And there hasn't been an alarm yet? Wow. Poor Tuscaloosa gonna get it again? Okay. We're almost through. 41 degrees, 36 minutes, 15 seconds. Hey, that'll sound an alarm. We'll get a cougar alert.
You know how cougar alert is on this.
We hear the alarms well though here. Okay.
Oh, you're talking outside, not here.
Yeah, outside, yeah. Okay, everybody got that one? Did we figure out a time? It's what? 15 minutes before clock noon, that would be
11:45.
11:45. AM or PM? AM, fantastic. Okay, how about Christmas Day? December 25th.
In the middle, noon.
What's our declination?
23 degrees south.
Second?
23 and a half degrees.
Yeah, 23 and a half. I think that would be close enough. South. So this time we'll do 56 degrees, 36 minutes, 15 seconds. Subtract 23 degrees, 30 minutes. And what do you get? 33 degrees, 6 minutes, 15 seconds. Close enough for government work. That's the noon altitude on Christmas Day. Doesn't get very high, about a third of the way up the sky, that's all. And it's pretty close to high noon. Less than a minute off. So 12 noon again. So you don't have to worry about opening presents, you know, if you want to wait till 12 noon. You don't have to say, well, is it really 12 noon or not? Clock noon and actual about right. Okay. Any questions? Okay. Now.
Did you grade our test the other day or no? Did you already talk about that?
I haven't finished grading them, no. I was working on the labs. Okay. And what happened was the only hours I've had of office hours since then was yesterday, and I had to work on making 2 practice requisitions because my computer printer cartridge died and another instructor's printer died, so I had to do 2 requisitions, and by the time I took care of other things, it ate up the whole afternoon, so I didn't get, I graded some last night, but I didn't get any graded during office hours. So while y'all are taking your test today, I'll be grading labs first, and then I'll get to the test. And as soon as I get them done, I should have, please let me have office hours tomorrow. I should have about 4 of them, and hopefully I can get most of the things entered there. Knock on wood.
How many questions
What's that? It's about like last time, maybe a few more or not. I don't think there'll be less. Let me see. We wouldn't want any fewer, would we?
No.
No, we want more, so they don't count off as many. Okay, right here will be fine. Thank you. Appreciate it. Thank you. And when you're through with them, I'll take them. Okay. Yeah. Okay, that's all right. All right, good deal. Thank you. All right. Let me see if I can find the test.
Here?
Yeah, right there will do.
I saw him, last time I saw him was like a month ago.
Goodness gracious. Well, let me see.
Really? Yeah.
I got them all. Okay.
Yes,
Can you believe it that we are through with Lab?
Yeah.
More than
Let's take the test now.
Let's just say
Can you go check it? Well, I guess
Let's
we're
take
gonna
the
have
test
to go
now.
there.
Can we take the test now? Or Tuesday?
What's that again?
Can we take the test now?
Yeah, that's what I'm going to say. Unless, I think that's just people letting out of class. The automotive students, as soon as they get out of class, they take out in droves. So that's probably what
yeah,
they finish about 3. I mean about 4. Okay. So you ready for the test?
Yes, sir.
Finish lab at more than an hour early.
You good,
life is good today.
About half hour early. A little over half hour early. So let me end this. Are there any questions before I turn this off?